Hey. All right. I will begin. Heavenly Father, we thank you for this day. I thank you for these students. Just pray you bless this class. Help us to learn a lot today, Lord. In your name I pray. Amen. All right, so I just want to get started. And this is, okay, so honestly, this is chapter 2, all right? So I still haven't talked about the kinematics in chapter 1, and I just can't talk about one-dimensional kinematics in good conscience until we talk about vectors. It's not in me. I can't do it. I'm sorry. So let's talk about vectors and position and coordinates, and then we'll talk about one-dimensional motion towards the end of today, okay? So technically speaking, yes, I'm jumping ahead to chapter 2. We'll come back and get the rest of chapter 1 in a bit. So let's just get started here. We think of an object as a particle, and what that means is that we think of the whole thing as if it were located at one point. We use a coordinate system to describe this, all right? So I've drawn some pictures of coordinate systems, and by the way, I will post this PDF in course content. I just scanned it about 10 minutes ago, so after class, hopefully I'll post it for you guys, okay? It's still a good idea for you to try to take notes while I'm doing this because studies have shown you learn by writing notes, most people, all right? So this picture illustrates indeed, three-dimensional coordinate system. So this is one of my chief criticisms of your text, all right? So if Captain Kirk had only had your text to study physics from, he would have fallen to Khan. Because you may recall, Khan was a genius, but he could only think two-dimensionally. But Captain Kirk, he thought three-dimensionally. I'm sorry, I'm ruining a whole movie for you that you haven't watched, obviously. But anyway, this is a classic Star Trek reference. Is there a new Wrath of Khan? Does it also involve two versus three-dimensional motion? I feel like I saw it, but I forgot what was in that movie. Fancy space aliens and ships and so forth, I suppose. Anyway, so getting back to physics, we can talk about a coordinate system. It has three dimensions. So in this coordinate system, there should be an origin, where the origin is where the coordinate 0, 0, 0 is. All right. So like in here, if I was to imagine setting up a coordinate system, we could do, oh no, how about like that corner over there? The corner, well, that could be the origin, right? And then what would the z-axis be? If that corner over there is the origin, the z-axis would be this corner right here, right? And then the x-axis would run that black strip along the wall out there, and the y-axis would be this guy up here, right? Except this awkward protrusion with this. We've got a cane. For some reason, is that one of yours? No. Okay. Anyway, so that's a coordinate system. So, for example, one of the precepts of physics is that you can set up coordinates, all right, and that they can meaningfully be calculated with respect to some observer, right? So what was your name? Marlo. Did I say that right? Okay. So we could try to figure out what her coordinates are. Let's say you're obviously an extended object, so we'll say the top of your head, like right here. If we were let's use feet since we're familiar with that, right? So I would guess that the top of her head as she's sitting down, if I had to wager, I'd say it's about 3 feet maybe? 3.5 feet, something like that off the ground. So the z-coordinate would be 3 feet. What would the x-coordinate would be? You know, you have to think about going over here and walking along this. The x-coordinate, I don't know, maybe it's about an x-coordinate of about 10, right? And what's the y-coordinate? Maybe about 15, something like that. Right, so to be more careful, we'd need, what, tape measure, something like that. But it's clear that you could do this, and this is the starting point. We can set up coordinates, and we can label points in space by triples, x, y, z, right? So there's a relation between spatial geometry, right, and these pairs of numbers, these Cartesian, what we call them triples of numbers. If we're just talking about a two-dimensional problem, we only need a pair of numbers, right, like x comma y. That you've done more in math already, right? You guys have graphed things with x comma y, right? Yeah. That's actually a relatively new idea. It was Descartes who had this idea that there should be a relation between numbers and geometry in this way, and started relating geometry to equations. It was the birth of what's called analytic geometry. We do a fair amount of analytic geometry in here. Anyway, this point has x-coordinate p1, y-coordinate p2, and z-coordinate p3. All right, let's move on. Sorry, I spent entirely too long talking about that. I will try to pick up the pace. So my main point is it's possible to set up a coordinate system and measure coordinates for the point where a particle is. That's great, but there's another concept we need, which is the vector concept. Now, some of you are biology peoples, right? Man, these tables are squeaky. That's good. That's just the sound of notes being taken, though. I accept it. So anyway, so a vector is a directed line segment, right? So it has a base point and a terminal point. So it starts at P and it goes to Q. That's the vector PQ, all right? Or you could say it's a directed line segment, right? So, great. What's the connection between vectors and points? Well, if we think about this point in three-dimensional space, there's a natural identification of that point as a vector which goes from the origin out to the point P, right? So we can identify a point. A point has no direction, right? A point's just sitting there. So if I can use Marlowe again, the point, don't worry, you're off the video, so it's safe. I mean, I'm assuming you might have a stalker or something, I don't know. There's all kinds of horrible things that could happen. It's important to keep you guys off video. So should I edit this out? Is it unacceptable? No, keep it? Okay. Sorry. You like it? I'm starting to, now see, that comment makes me think I should edit it out. I don't know. But the point is, I was getting to a point, which is that there's a point here, right? That's a point. Is there a direction to that? No, I mean, it's just a point. But we can also think about the point at the top of our head in terms of a directed line segment back from the corner that points up to it, right? And if I had that vector, it's the same as having the point. We can trade back and forth between a point and a vector from the origin which points to that point.
Wait,
all right?
Are you talking about the base point or the terminal point?
The terminal point. So if we put the base point at the origin, then the terminal point for the vector can be identified with the vector. But that, of course, assumes that the vector is where it's based at the origin, right? So, but that's something we often do. So you might sometimes in here, I might say it's a point, I might say it's a vector. There's we can go back and forth between these two viewpoints. That's an unfortunate terminology at this point. Oh no! I'm sorry. My best puns are unintentional. So the basics of vector math, let's talk about it. We can add vectors. Geometrically, the way that's done is tip to tail. So what you do, here's vector A, vector B. We start at some point. We put A there, all right? So I'm already introducing the idea that we can move vectors around, right? We can move their base point somewhere else. It's not really, I mean, yes, given a base point and a terminal point, we have a directed line segment, right? But we can move that directed line segment along. I mean, this is our viewpoint in physics, is that if you think of my arm as being a vector, then it's the same vector whether it's here or here. I'm from the elbow up. Or here, or here, or here, you know? It's the same vector. I'm sorry, I should be using, what am I, here. Here's a vector, right? This vector is the same here as it is here in terms of its magnitude and direction. Okay, they have different base points, right? But we think of those as being the same vector in here. That's one idea you should be aware of. So what I'm thinking of is I'm taking this vector A, I'm moving it over here, I'm taking the vector B, I'm attaching the tail of B to the tip of A, and this is what we call A plus B. It's the sum of the vectors A and B. The green vector is what we call the resultant. All right? Now I have a couple more additions for us to look at. Let's see here. This time I'm going to try to keep with the same A and B, but I freehanded this, so if you think it doesn't look quite the same, you're probably right. So You're like, couldn't you have just gotten up out of your chair and got a ruler so it would have been better? It's true. I could have, but I didn't. So you can put that in your course evaluation. Teachers should use ruler. You know, save that. Remember that to put in your course evaluation so that, you know, you can set me straight. But just make sure it's in the first 5 words you write in the text bubble, because that's about all you get. So, it's a source of constant frustration for me. Like, I'll have a student be saying, the way this course could really be improved, blah, 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 if, and then that's the end of the text they're allowed in the course evaluation, right? Because you got like 50 characters. So my courses never improve. Oh, well. This course is infinitely better than the last time I taught it residentially, though, in the regular semester. So that's a joke. I've never taught this residentially in the regular semester before. I taught it in the summer once. That worked. So here's A, and here's B, here's A. So what I'm adding is 1 copy of A, then plus B, and plus A again. So what we're looking at here is A plus B plus B plus A, also known as 2 copies of A plus 2 copies of B. All right? Could you have added the vectors in a different order and still got the same resultant? Yeah, you could see that, right? If I had instead started by adding the 2 B's together and then added the 2 A's together to make like a big old L, we would have still got the same resultant, right? That's because vector addition is commutative. We should also talk about the idea of the negative of a vector. What does it mean, minus A? So if A goes up like this, minus A is the same magnitude but the opposite direction. This is called the reversal of a vector, 180 degrees around. So here's A plus B minus A minus B. And you can see geometrically, right, that resultant is just B. But you know what? Algebra also does that, because A plus B minus A minus B, well, check it out. The B's cancel, and the A's cancel, and we're just left with 1 copy of B. So you could either see that algebraically with what I wrote in green, or you could see it graphically, right? There's these 2 different sides to the same coin. We can do graphical analysis of vector addition, or we can do algebraic analysis of vector addition. All right? Here's a question for you. What if we had vectors that pointed along the edge of a regular polygon? Like, suppose you had vectors that made a triangle. What would the sum of those vectors be? Let me save that question for when I can write it on the board later. The answer is 0. Oh, no, I told you the answer. I'm so sorry. Not being able to write as I'm talking, it's suffocating to me. So I'm eager to get through this, but I should stick with this. I have a plan. All right. So now that we have this concept of a vector, we can talk about the vector that connects 2 points in space, right? I mean, I already introduced that. PQ is the vector that connects P to Q, right? But let me talk about how to calculate that specifically, component-wise. So if you look at this vector from P to Q, you've got, look at this, you got a vector P plus the vector PQ, right? So we have P plus PQ, right? If you look at that, this plus that is the same as Q, right? So P plus PQ equals to Q. Therefore, we get that PQ is Q minus P. If you want to calculate the vector that goes from P to Q, you take the difference of the Q vector and the P vector. All right? Now, this is important because this is how we calculate what's called displacement. Actually, I'll pause for a second here. I think some of you are still writing. Any questions about this?
Can you go back to your example as to why asking us about the vector being outlined by the triangle and it being 0?
Oh, I'm going to write that on the board. Remind me to write that on the board when I start working on the board a little bit. Hopefully sooner rather than later. So keep that question for a bit. Yes, I'm planning to post these right after class, as long as I don't get distracted. If I have not posted these, by like the Gong Show tonight, you should make sure to like contact me. You guys are not big devotees of the Gong Show? No? Oh, you guys don't watch TV. You're young, right? No? You're old? Seem young. I need some way to connect with you guys. Do you guys watch Rhett and Link? Rhett and Link? What is it? It's a YouTube show. It's like the longest ongoing YouTube morning show. Well, it's called Good Mythical Morning. I don't know. Is it a morning show? I guess it depends on when you watch it, right? I think mostly they're famous for eating a variety of things that ought not be eaten, right? So, fun story, they were the MCs for Campus Crusade for Christ when I was at NC State in the late 90s. So that was my introduction to Rhett and Link. Before the internet really got going, they used to come in and they would be like the masters of ceremony for Campus Crusade for Christ. Or how is it known now, since we can't have crusades? Oh, Cru, yes, Cru. But you guys still call it Campus Crusade, right? I've heard that, anyway. So they were very funny, and I mean, under their leadership, I think Campus Crusade grew from like 150 people when I started going. By the time I'd left NC State, it was up to like 800 people. It was insane. It was quite a meeting. And then all of a sudden, I saw a Super Bowl commercial last year, and I'm like, is that Rhett? And then I learned, oh, they've had this YouTube show since like 2012, and they've got millions of followers, and it's actually like kind of a big deal. Like, you guys actually know who he was. I thought it was kind of funny, because I met them in person a long time ago. But anyway, I don't think they know who I am, but that is fine. All right, so anyway, moving on. If we have, so we're primarily interested not just in vectors in the abstract. I mean, just the geometry of vectors is interesting and all, but what we're really after is describing the motion of physical particles, right? So the first idea is that we can think about a particle being there and a particle being there. So position 1 and position 2. And what I have in mind is like one object that's moving from R1 to R2. So we could give it a name. You want to give this particle a name? What's that? You get a name? Ah. No one's going to, we can call it, I mean, yeah, we're going to give it a name. Lex. Okay, so Lex is, at time 1, Lex is at R1. At time 2, Lex is at R2. That's an interesting choice. Is it like your nickname, or?
That's her nickname.
Oh, it's her nickname, okay. Ooh, nicely done. Yeah. That's how you do that right there. That's, exactly. So, Lex is at R1, Lex is at R2, at time 1, and this is at time 2. So I'm drawing two different moments in time in this one picture, okay? The displacement from R1 to R2 is delta R. So this triangle is read delta, or change. So the change in R vector is R2 minus R1. This is the displacement. Displacement is a vector, and that's how you calculate it. An event, by the way, is a time and a place, all right? So we're talking about two events and the displacement going from one event to another. Here's some terminology. The ending position, the starting position, the displacement. To get to the ending position, you take the starting position and you add the displacement. All of these things are vectors, all right? So here's the situation. A particle goes from position R1 at time 1 to position R2. At time 2, we define, I just said this, I'm saying it again, delta R, R2 minus R1 is the displacement. Delta T is the duration, or the change in time. I believe your textbook calls it the time elapsed. See, I can't say it. Can you get somebody say it for me? Time elapsed? Goodness, I cannot say that today. It's the worst. Elapsed. What's wrong with me? Many things. But anyway, so the velocity, delta R, delta T, is the change in the displacement, it's the change in the position divided by the change in time. Now, technically speaking, this velocity that I've just introduced is the average velocity, all right? If you want me to be, more picky, honestly, the velocity should be thought of as the instantaneous velocity. What's the difference between average and instantaneous velocity? Well, instantaneous velocity is defined in terms of a limit, right? So this is part of that pesky thing called calculus, which about half of you have heard of, and the other half of you have avoided. So that's fine. Teach his own. I'm sure you know more about genetics than I do. Let's see here. So anyway, this is a limit. But intuitively speaking, you can just think of the instantaneous velocity as being the average velocity where the increment of time over which it's measured is really, really small. All right? And in fact, instantaneous velocity you're not unfamiliar with. The magnitude, and by the way, magnitude of the instantaneous velocity, magnitude of a vector is the length of the vector. So the magnitude of the velocity we call speed. So in your car, right? Some of you have cars, I'm assuming. Some of you have a car old enough that it's got this like analog speedometer on it, right? Little thing goes back and forth, tells you how fast you're going. That would be an example of instantaneous velocity to a pretty good approximation. I mean, it's telling you how fast you're going right then, right? So, and this is how the police judge velocity, right? Like if I'm going 100 miles per hour as I'm about to pull into my driveway, and I tell the police officers, well, sir, my work is 10 miles away from my home, and I've only been in the car for 10 minutes. It will concern him little that my average velocity was 60 miles per hour. The 100 miles per hour that I was doing when I passed his speed trap will be all he cares about, right? So like instantaneous velocity is the velocity we think about often. Average velocity, though, is something we can calculate without calculus. All we have to do is calculate the displacement divided by the duration. I think it's about time we had something with numbers in it. Here we go. Example. So at 3 seconds, we have position 3, 2, 1, m. What's that m? Meters, right. So you could just as well have written 3 meters, comma 2 meters, comma 1 meter. But what did I do? I just wrote meters out to the side. So if you do that, it's understood that meter multiplies every component, all right? And then at time equals 7 seconds, we have observed that Lex, right? Yeah, Lex, was at minus 6 to 8 meters. Now, minus 6 is minus 6. That's like the other room. I mean, I guess it's a bathroom. I don't know. I mean, I'm not sure. I can't tell. But I don't know, is there another classroom over there? I think it's a hallway. I don't know what it is, but anyway, that would be on the other side of the wall. And so we have these two events, this position at 3 seconds, that position at 7 seconds. And the question that I'm asking is to find the displacement, the duration, and the velocity. All right? And so here's how we do it. So R2 minus R1, that's 321 meters, minus 628 meters. And so just to make it confusing, I put the meters inside just to bother you. And then how do you subtract vectors? You subtract them component-wise, right? So like 3 minus a minus 6 is the plus 6. 2 minus 2, 1 minus 8. And so we've got 9 meters, 0 meters, minus 7 meters, right? And then I just decided to pull the meters back out again because, I don't know, I'd rather write 1 and 3 of them. Yep. Did I flip them around? Nah. Oh, man. Oh. Let's do it on the board. Yeah, we'll. Yeah. Well, let's see here. How to fix this? I mean, what she's pointing out is that I have accidentally exchanged R1 and R2. So what I've calculated here is not delta R, it's minus delta R. All right? Listen, I will make a correction to this and then post the corrected version, okay? Yeah? But, so, in other words, if we corrected the calculation, the right answer should be, so if you just tried to do it on your own and didn't look what I was doing up here, what you should have got is minus 907 for the displacement. The duration, or the time elapsed, still can't say it, is 4 seconds. 7 minus 3 is 4. And the average velocity, this will be an error because I made that mistake, right? So the average velocity would be like minus 9/4 meter per second, 7/4 meter per second. Again, I got to fix my minus sign. So the correct answer should be minus 2.250, 1.75 meters per second. That's the average velocity between these two times. Again, sorry about the sign error. All right, speed. So the speed is the magnitude of the velocity, which is the length of the velocity vector. The way to calculate the speed is you take the square root of the sums of the squares of the components. All right? And so, good news, that sign error doesn't mess us up. Like if you, what's the length of A? What's the length of minus A? I mean, it's the same. What's the length of A? What's the length of minus A? It's the same length, right? So if you reverse the vector, it doesn't change its length. So my sign error for the velocity won't change the speed. The speed will still work out to the square root of 2.25 squared, 1.75 squared, which is 2.850 meters per second. Now, when I write this, I mean it's approximately that. It's actually, that's like I told you guys, I'm going to try to give answers with four numbers, 4 decimals for the answers in here, just to have a common kind of thing to compare. All right, so velocity versus speed. Velocity is a vector. Speed is a scalar. A vector is, again, it's got 3 components in 3 dimensions, or if we talk about 2-dimensional vectors, as we usually do in here. This is one of the only days I'll really talk about 3-dimensional vectors. For the most part, I'll be in 2 dimensions or 1 dimension. So my apologies if the future lectures seem more flat. But I don't understand you guys. I've told much better things today than that. I don't know. I gotta do some reading. All right, so speed is a scalar. That means it's just a number. All right, and speed is, by the way, positive. If somebody tells you, my speed was minus 30 miles per hour, you should say, you don't know the definition of speed. That's impossible. Your velocity was minus 30 miles per hour. Your velocity could be negative. Your speed must be positive. It could be 0, right? Most of you have a speed of 0 with respect to the reference frame of this room, right? But you have a non-zero speed with respect to other reference frames, right? Like if we took the reference frame of the sun, the Earth is moving around the sun, right? So you have speed with respect to that reference frame. I don't emphasize this too much today, but everything is based on a choice of a reference frame, right? So you could be still in one reference frame, but moving in another. I'm assuming you've all ridden in cars before, right? Unless you're like one of my children, you're at rest with respect to the car, right? Sometimes children, they reject this principle and move around, but setting that aside. All right, so the math is this. The length of a vector is the square root of the sum, it's the square root of the sums of the squares. You've probably already learned this for 2 dimensions, right? Like this is the distance formula. If you want to calculate the length of a triangle, it's the square root of the adjacent side and the opposite side, right? The square root of the sum of the We take the square root of the sums of the squares of those, gives us the length of the hypotenuse. This is called the Pythagorean theorem, right? Or a squared plus b squared equals to c squared. This is just the generalization of that to 3 dimensions. All right. So the distance between R1 and R2 is the length of the displacement. Now, this is a dangerous thing I just said, because sometimes you're asked about the distance between 2 points, all right? Other times you're asked about the distance traveled between 2 points, right? So let's see here. For example, what's the distance between this point and that point? By definition, the distance between those 2 points is like the shortest line, the length of the shortest line that connects it. It's maybe about 10 feet, right? What's the distance traveled by me as I'm going between these 2 points? I'm going to do this until you laugh. Okay, that worked. All right. Whoa. That was a bad idea. Whoa. There. Obviously, that distance was longer than 10 feet, right? So distance traveled is not the same as distance between. The distance between 2 points, we could also call the straight line distance, or sometimes you call it as the bird flies, if you're like from another generation or something. So beware of that terminology. So distance traveled is, you know, if I had been like a spider, you know, laying a web as I was walking, and then you could take that web and like lay it out straight, the length of that web, that would be the distance traveled, right? It's also the arc length of my path. Now we can talk about average speed. The average speed is the distance traveled divided by the time that elapsed. I'm going to stop trying to say it. The duration. I digress. Next, acceleration. What's acceleration? If we have 2 events, right, you can talk about the acceleration. The acceleration will be defined to be the change in velocity divided by the change in time. That's the average acceleration technically. If you want the real deal, you need calculus. It's the derivative of the velocity with respect to time. But again, acceleration is a vector. So here's a picture. You know, this is the path of some object, this gray wiggly thing, all right? And so the green arrows I've drawn to illustrate the velocity, right? The velocity points tangent to the path, right? What's tangent mean? It's like it's the line which just barely touches what you're talking about, right? And then just kind of goes off straight. So it kisses the curve, but just like that. And so this is, I've done my best to try to draw V1 and V2 in sort of the direction of the tangent of the path. Geometrically, that's what has to happen. It doesn't really matter that we don't know calculus and can't describe that carefully. We still have an intuitive idea what a tangent is, right? You guys familiar with slingshots? So like, you know, you slingshot like the class, not these lazy rubber bandy things. That's too easy. No, I'm talking about the kind that King David probably used. Well, not king at that time, right? So here's your biblical integration for the day. Pay attention. So, you know, he had what, like a leather strap, another leather strap, a little pouch, and then, right? And then let it go. And then at the right moment, that stone comes out of the pocket, and what does it do? It just keeps traveling in a straight line, right? Tangent to the circular path that it was going before he let it go. So anyway, I think I'm starting to get into another lecture altogether there, but tangents. So the displacement, again, the change in the position, the time elapsed, the velocity is the displacement divided by the, oh, I'm sorry, my calculus is showing. Don't worry, that's just a typo for us. So the velocity, the change in the position divided by the change in time, and then the acceleration is the change in the velocity divided by the change in time, so the delta v delta t. Again, speed is distance traveled divided by time elapsed. All right, so I hope I have said. Here's an actual numerical example. Let's see if I could actually get the sign right this time. Moment of, I don't know. Suppose we have position 128 at time 1, time 2, t1 equal to 2 seconds. And at that same time, the velocity is measured to be 310 meters per second, right? Whereas the second, at time 2, we measure velocity 601, all right? What's the acceleration between these two events? Well, we take v2 minus, hey, check it out, I figured out how to take v2 minus v1 now. Yeah, I blame the child. I think a child must be responsible for the other sign error. Some child did something to me and distracted me. I don't want to blame the children, but let's blame the children, right? So yes. Which one should I blame? What's that? You've got, yeah, Benjamin. You got your Benjamin. You got your Matthew. You got your Isaac. You got your Daniel. You got your Hannah. Matthew's a good choice. It probably was Matthew. He was kind of rascally yesterday. That's a good. Okay. Although Benjamin has just acquired the height that he can walk up to my recliner while I'm working on the computer and go, and they go, and then walk away. So if I ever have like an announcement that seems really odd and it's like half written, and then at the end of it it's like, that's probably Benjamin. Yeah. So the acceleration, we take the change in velocity, which is itself what? It still has the units of velocity, right? v2 minus v1 is a vector in meters per second, right? The time elapsed is 2 seconds. I just said it. What did I do? I still did something?
Why is it 6 minus 4 and not 6 minus 2?
Ah! Why can't I just do it right? Ah! It's almost like I make these errors to see if you're paying attention. Would you believe it? No. Okay. Yeah. So the easy way to fix this is to cross this 2 out and put a 4 both of these places. That's what I'll do in my correction. I'll change t1 to 4 seconds. Then this makes sense. If you make this 4 seconds, make this 4 seconds. By the way, this freedom is only allowed to me. You're not allowed to change numbers in the problems that I assign you on the test. Just saying. I mean, if a test question doesn't seem to make sense, you should ask me. All right? Like, are you sure you meant this? There doesn't seem like there's enough information. I'll be like, there's 2 different possible outcomes. The one is like, oh no, there's not enough information. The other is, maybe you're using the wrong equation, right? But I don't mind if you ask me. If a question I've written on the test doesn't make sense to you, you should ask me about it, right? Don't just labor in silence. Okay, so anyway, after I change the time 1 to 4 seconds, because I'm an idiot, we get an acceleration of 1.5 meters per second squared minus 1.5 meters per second squared, comma, minus 4.5 meters per second squared. Again, acceleration is a vector, all right? What are the units on acceleration? Meters per second squared. What are the units on velocity? Meters per second. What are the units on position? Meters, right? These are all SI units, right? So we're almost to the bored part of the talk. So I mean, I hope you're not bored. Oh, I'm sorry. This is still horrible. Too horrible. So that's about all I have to say about vectors at the moment. We'll come back to it probably Tuesday, okay? Mostly I just wanted to set the stage for one-dimensional motion. So one-dimensional motion, a little bit different. For 2 or 3 dimensions, we need vectors. They're necessary to describe position, velocity, and acceleration, all right? So the term deceleration is really hard to understand in more than one dimension, right? Like, what if I'm going like this? Am I decelerating? I don't know. I mean, it looked like I accelerated in the x direction. I think I decelerated in the y direction. So which is it? Did I decelerate or did I accelerate? Decelerate's a dangerous word. Let's talk about acceleration, all right? So position, velocity, acceleration. Speed is the magnitude of the velocity, which is also the distance traveled divided by the time. It is a positive scalar, which means number. What are the units for speed? Yes, still meters per second. Of course, we could also talk about miles per hour or feet per minute if you're really weird. I don't know. People who make BB guns, they like to talk about feet per second because it sounds more awesome, right? Hundreds of feet per second. You know. All right, anyway, I digress. So for one-dimensional motion, we can use a sign in the sense of plus or minus to denote direction. All right? So, and this you probably already know, if this is a one-dimensional system, if we have x equal to 0 here, we have x positive over here, we have x negative over here by our usual conventions. I mean, assuming that right is positive. We could set up a coordinate system where the positive direction goes that way. Wait a minute, that's my right. What's your, well, we got to make it, we could make, wait a minute, so if I'm thinking of you, that being positive direction would be weird, right? Because that's like the left direction. We could make the positive direction be down, right? We can make the positive direction be up. We can make the positive direction be any which way we like. We just have to define the coordinates to do that, all right? But by default, we choose right to be positive and up to be positive, right? I mean, that's the standard practice. Now, velocity here would be delta x over delta t. And you might say, well, that's not a vector. And fine, yeah, I mean, in some sense, it's not a vector. It's just a one-dimensional vector is a number, all right? So that's where these vectors and numbers kind of get intertwangled in one dimension. So it's harder to tell the difference. But here's the difference. Velocity can be positive or negative, but speed is always positive, right? The speed is the magnitude of the velocity. And in one dimension, that's just absolute value. So the velocity, average velocity again, delta x over delta t. Sorry, trying to get on with it here. And I think we've come to the end of my prepared slides, which is for the best. So here's two situations. The one at time 0, I'm afraid to even check the details here. I feel like Matthew might have come back. I don't know. Let's see here. So for time 1, I'm at 3 meters. At time 2, I mean Lex is at 10 meters at time 2. Oh, time 2 is 14 seconds though. So what's the velocity? We do 10 minus 3 over 14, which gives me 7 over 14, which is 0.5. 0.5 meters per second. That being positive is, what's that mean? That means that the motion was rightward, right? On the other hand, this motion, going from 6 meters to minus 4 meters, from time t1 equals to 4 seconds to t2 equals to 8 seconds, well, when you calculate the velocity, we get what? Minus 4 minus 6, which is minus 10 over 4, which is minus 2.5 meters per second. So that negative velocity means that motion was left, right? What is the speed in case 1? The speed is 0.5 meters per second. What's the speed of this object in case 2? It's 2.5 meters per second. We just throw away the minus. That gets us the magnitude of the number, which is the length of the number, right, on the number line. All right. So now I got that out of my system. Let us change gears a bit. Now I gotta, this is the, so I think for the most part here, guys, I'm going to try to lecture as I'm about to start lecturing. I think this is going to be a better format for us because, well, it's fun to see errors that I've made on slides that I can't fix. It's much more fun to see me make errors in real time. time. Whoa. Cool. Nice. Oh, look at that. See, it goes. See, watch the. I think I better. I better turn down. Like, no, go back. Wow. Oh, that. No. Ah. Yeah, that's why the mic level has to go down. Otherwise, hopefully this is going to work. We'll see. All right. How about now? Is that a reasonable volume? I think so. So I think you guys could see over there. Let me try. So here's what I'm torn. Should I turn the lights on up here so we can see the board better? I mean, I wonder what's the right. See, but then you can't see the. So I'm kind of. I think I need to bring a light. Right? Yeah. But anyway, I think if I use black over here, you guys will be able to see me, right? Is it gonna? Oh, well, see that is unfortunate. I wish I don't know how to get all this meta stuff on the phone to disappear. I mean, phone, listen to me. Well, I'll fuss with that after class. Maybe we'll figure out how to fix it. Hearing myself after I talk, it's weird. So, does this show up? Does that show up over there at all? God. No, it's the lights not being on. All right, I'm gonna bail on this for today until I can fix it. And by bail on that, I mean there you go. You're now in charge. There we go. So guys, do you have any questions about particular homework problems that I've assigned you? All right, well, let me just go ahead then. So for one-dimensional motion, we have v is equal to dx, change in x over change in t, right? So this is the average velocity. If the acceleration is equal to a constant, right, what would that mean? That would mean that the final velocity minus the initial velocity divided by the change in time is equal to that constant a. So we can solve that equation, right? And this gives us that the final velocity is equal to the initial velocity plus the acceleration times the change in time. This is one of the kinematic equations that we need to solve problems with, okay? It's a very, very important equation. Another equation that we're going to need to know for constant acceleration, so I'm talking about constant acceleration. I mean, if the acceleration is 0, it's even easier. Like, how is position and velocity related if acceleration is 0? What equation do we get? We just have this. Well, if the acceleration is 0, then the velocity is constant, right? So that tells me that the distance is equal to the velocity times the change in time. But this formula right here, this is for a equals to 0 only, right? So if the, so to a reasonable approximation, if I, ignoring friction and just focusing on the horizontal motion of this marker, that is more or less delta x is equal to v delta t. Whatever initial horizontal speed I gave to the marker, it just keeps going that way, right? Whatever delta time there was. So actually we could figure out how fast I threw the marker by if we knew how long it was in the air, right? And how far, well, I don't know, these words. Let's see here, what would if I knew it took, let's see here. If that, where I just got to, was 30 feet, right? And I knew that the marker was in the air for 1 second, then what was the speed with which I threw it? Right, 30 feet per second would be what I threw it. Because there's no x acceleration, right? Now, on the other hand, if I think about vertical motion like this, right? So check this out. Whoa. Well, I tried. Let's try again. Whoa. So the displacement of marker before and after I threw it is 0. So the average velocity is 0. So can I use delta y equals v delta t? I cannot, because what is happening with this motion? Is this constant velocity motion? It is certainly not. It is constant acceleration motion, though. The constant acceleration is minus g, which is due to gravity. All right? So the formula for constant acceleration, so when there is acceleration, the velocity is changing. And you can derive also that the final position is equal to the initial position plus the initial velocity times time plus 1/2 the constant acceleration times time squared. Now this formula I just wrote, all right, fine. I should put delta t here. A lot of times I like to just think of delta t being equal to t, because then the formulas are sort of easier to look at, right? And I just think of, if I think of the initial time being time 0, then it makes sense to just say delta t is t. If you don't mind, I'm going to write these formulas in terms of t because they're just a lot easier to look at, okay? So I've written the formulas for constant acceleration in the x direction, but like I just told you, it's not usually the case we have that. If we want to think about the vertical direction being, well, I had written z earlier, but we usually think about it being y, because we're usually just thinking in 2 dimensions, right? We think about like one horizontal direction and then up and down being vertical. That's kind of typical. So if the acceleration is equal to, sorry, I'm getting ahead of myself. So let's suppose for vertical motion, we write this. We say y is equal to the final y, right? It's equal to the initial y plus the initial velocity times time. Oh, I'm sorry, I'm not wrong, I'm just not done. Minus 1/2 gt squared. So here I'm assuming that the acceleration is equal to minus g. What is g? G is gravity, all right? It's the gravitational acceleration. So for the moment, we'll just take this to be an experimentally determined fact. If you take objects close to the surface of the Earth and you drop them, they accelerate downwards with an acceleration of about 9.8 meters per second squared, right? Depending on exactly where you are relative to the equator and such, but so this is minus 9.8 meters per second squared because we're on Earth. And it varies by about 1/10 of a meter per second, depending on where you are and stuff, right? There's an altitude dependence. If you could go really high up, gravity gets weaker, right? Earth's gravity, if you're on the moon, it's probably negligible, right? It gets small really fast as you get away from the Earth. On the other hand, it's the gravity of the sun that keeps the Earth in rotation around the sun, right? So gravity does have long-term, I mean, it has long-distance effects, right? But it takes a lot of mass to get enough gravity to make a long motion happen. Okay, anyway, so y, the final y is equal to the initial y plus v naught t minus 1/2 gt squared. And also we have the formula for the velocity. It's v naught minus gt. So these two equations are very helpful if we're trying to solve problems that involve vertical motion where we're talking about there being acceleration due to gravity. Let's look at an actual problem with some words and stuff. I guess I'm working on this board. I washed my shirt, can you tell? See? Grease lightning, yeah. It smells good. Whatever. All right. Here we go. So imagine Mr. Top Hat. All right. He's standing here. Let's suppose that he's at y, his feet are at y equals to 0. All right. And he has a ball. All right. And he throws it. Yeah. All right. And suppose he throws the ball with a velocity of 2 meters per second upward. All right. And suppose that balls. Let's see. Yes. Suppose that the ball is thrown from an initial. So Mr. Top Hat is. He's really tall. Let's say. Okay. So let's suppose he throws the ball from 2 meters above the ground. Oh, I don't want to have 2 also. Let's say. Let's make it 3 meters. Wow, he's really tall. So suppose that this is 3 meters. So he's throwing the ball with an initial upward velocity of 2 meters per second, right, from an initial height of 3 meters. I guess he has stilts or something. I don't know, right? Do you know any people 3 meters tall? How tall is 3 meters? Do you guys know? What is a meter? How does a meter relate to a foot? What's that? Yeah, almost right. I think it was 3. I remember 3.281. Is that right? See, it's disappointing that I know that number because I really should, as I've said last class, know other numbers that are more important. And yet, this useless information like meter to foot conversion is stuck in my head. What's that? 3.281, yeah, that's what I said. So an inch is 2.54 centimeters. The sun has a mass of 1.99 times 10 to the 30th kilograms. The Earth has about 6.38 times 10 to the 6th meters mean radius. A mass of 5.94 times 10 to the 24th kilograms. Why do I know these numbers? Who cares? Anyway, I was a physics major undergrad. It gets ingrained. But the question to you guys, so this is given, this stuff's all given. Now my question is, how high does the ball go